This short video explains about a concept of Schur complement, which is a function of a matrix to another matrix. Okay. Suppose we have a matrix. Okay, let me just remove this first. Suppose you have a matrix X that partition into 4 blocks A, B, C, D. Okay, everyone should be familiar with the block notation, like this. Okay, you can call this guy you can call these 1 leading blocks as A. Of course, these partition as B. Okay, these 10 as D, and of course, certainly this is a C. Okay, so when you have X and into these 4 blocks, the Schur complement is defined in 2 different ways. The first way is that we call the Schur complement of D in the matrix X. X is kind of the whole block, the whole block, and the size of A, B, C, D must agree in a sense. For example, A and B must have the same rows. Okay, and C and A should have the same columns, for example. So we call the Schur complement of D in the matrix X is defined as A minus B D inverse C. Okay, I try to kind of mark the flow of of this of how different how the matrix in different blocks are are composed together to define the Schur complement. Of course, this definition exists if D is invertible, as long as the determinant is non-zero. You would see that suppose X has 4 blocks, and suppose A is, of course, A has to be square in this sense. Okay, doesn't have to be. Hold on. So D has to be square. Okay, first of all, let me assume that D has m by n. Okay, and suppose A is n by n. D is m by m. Oh, let me just use another variable so that my pronunciation is clear. D is r by r. A is n by n. Okay. Now, you see that my S that has this definition is gonna be a matrix of size n by n. Okay, I mean this term need to have the same dimension as A. Okay, but in order to of course, let's just verify the dimension and everything. If A is n by n, D is r by r, B need to have size n by r. Same rows as A, same columns as D. What about C? C need to have size r by n. Okay, in order the whole block partition makes sense. Okay, so the term very simple. I'm just verifying the dimension. So B D inverse C is going to be n by r times r by r times r by n. So the whole thing is n by n. All right. So S is actually a mapping from a matrix of size size n by r times n by r to a matrix that has size n by n. So you can take a look at this as a nonlinear matrix transformation from a matrix that has bigger size to a matrix that has smaller size. Okay, this is called Schur complement of D in X. And we're going to show later that once the Schur complement defined this way, we can prove that determinant of the whole block X is actually related to determinant of the Schur complement and determinant of D. Okay. In another way, there's a second definition of the Schur complement. We call it the Schur complement of A in X. So it's defined as, if you look at the formula, it's defined as B minus C A inverse B. Okay, so of course, again, the same condition that the Schur complement of A in X is valid if A is invertible. Okay, so now we have two different ways, and the two different Schur complement will have different sizes, actually different matrices. Now, let's see how these results can be shown. Okay. So here, before we see the result, we assume that you know a little bit about matrix decomposition, and LDU is one of them. A matrix can be can be decomposed into a lower triangular, a diagonal matrix, and upper triangular matrix. This is called LDU. Okay. Now, the result of the Schur complement can be shown by this analysis, and it gives us some a very important result that is called matrix inversion lemma as well. Okay. I would like you to take a look that if X can be partitioned into A, B, C, D, okay, you can decompose in LDU decomposition this way. Okay, so I'm not going to give the detail of the derivation, but I just want you to basically multiply these three terms, and to make sure that it actually equals to the left hand side. Okay, so hold on. So you see that this is identity, right? So so this is L. So because it's upper, sorry, yeah, U, okay. And this is, you have 0, 0, so you see that this is a block diagonal, so you call it D, okay. And the matrix here is actually, it has identity in the main diagonal block, so you represent it as a lower triangular matrix. Okay. From here, you already know that because the main diagonals of these U and L, the main diagonals are identity matrix. So immediately you know that the determinant of U and determinant of L has to be non-zero, actually equals to 1. Okay? Or in other words, these two guys are invertible. What about D? D are diagonal blocks. D have diagonal blocks. So the inverse of D exists if, of course, if the main diagonal blocks are invertible. So if we move to that assumption, if D and this guy, okay, this term A minus B, D inverse C, is actually the definition of the Schur complement that we see previously. Okay, so now we're going to make an assumption that if D and S are invertible, of course, you can just inverse the whole thing. Okay, so it's going to be, so if you inverse the whole thing, so it's going to be this term inverse first, and then this term inverse, and then this term inverse. Okay, you know that lower and upper triangular, when you find the inverse is also preserve the triangular structure. So when this guy is lower, the inverse is also lower triangular. This guy is upper, the inverse is also upper triangular. And the inverse of these L and U, you can verify it yourself. You know that the expression is given by this and this. And of course, the most simplest one is the inverse of the diagonal block. Okay, so it's going to be S inverse and D inverse. If you multiply the three terms, Okay, if you multiply the three terms, it's not hard at all. Just multiply these two first and then multiply with this. It gives us the last line. That is called the last result is called the inverse of a block matrix, and it is called the matrix inversion lemma. Another way to inverse, the whole block, you can also partition into 4 blocks, and all these all each block can be just given by a function of a, b, c, d, and it involves the Schur complement of d in x. Okay. Now, so this is the definition of Schur complement. We would like to show this box, the orange box, that determinant of x equals to that d and that s. This is very obvious from the LDU composition, because determinant of x is actually the determinant of this guy times determinant of this times determinant of this. But the determinant of L, factor L and U is, of course, is equal to 1. All right. And the determinant of the diagonal block is the determinant of diagonal matrix. Block diagonal matrix is, of course, determinant of A minus BD inverse C. Is actually equal to the diagonal of, the det of the main diagonals. And that proves that determinant of x equals to the determinant of the Schur complement multiplied with determinant of d. Okay. The Schur complement often find the application in a special case when we have a matrix that is symmetric. Okay, in this case, it's just reduced to the form that the Schur complement, this is the Schur complement of d in x, this is the Schur complement of a in x. Okay, did I say the other way around? Oh, okay, right. This is the Schur complement of d in x, this is the Schur complement of a in x. Okay, 2 different Schur complement form. Even more, okay, from the fact that we have seen before, determinant of x is equal to determinant of d times determinant of s equals to determinant of a, determinant of s2, s1 and s2. Now, if x is also a positive definite matrix, what can we say? What more can we say about the Schur complement? This is also positive definite as well. Okay, now let's go back to here. Okay, now we consider the symmetric matrices, right? So, okay, how about if we know that x is positive definite, okay, what do you see here? Suppose you call this guy U, okay? Of course, this is U transpose, okay? And you have some matrix here, okay? And of course, this is a form of X equals U, you call it U transpose, okay? So if X is positive definite, but since the determinant of U is 1, which means U is invertible. Okay, so X is positive definite if and only if M is positive definite. Okay, but M is a block diagonal, so M is positive definite even only if all the main diagonal blocks are positive definite. So it means that this M is positive definite even only if S is S and D are positive definite. Okay, so we have this result. Okay, and of course we talk about some special case. If X is merely positive semi-definite and D is positive definite. Okay. Now we talk about the case that we include the case that X could be invertible. Assume this is the assumption: X is positive semi-definite and D is strictly positive definite. Then that condition, okay, will result in the conclusion that the Schur complement could be positive semi-definite. Because if the whole block diagonal is only positive semi-definite, the positive semi-definite and positive definite, okay, these two cases only differs by the fact that when X is positive semi-definite, it means that X could be singular, which means determinant of X could be positive. Could be 0. That is the case that the null space of X is non-zero or subspace. Okay, now, so if the orange block is positive semi-definite, but by the assumption the matrix D is positive definite, so we conclude that the term that makes M positive semi-definite must come from the Schur complement. Okay, so that's how we get the second conclusion. Okay. Okay, and this is the conclusion from the Schur complement of D in A. Okay, another results can be concluded as well for the Schur complement of A in X. This is for S2. Okay, now I would like to mention a little bit how we can in what circumstances we would see the use of the Schur complement. The very first one is simple. This is how we, when you perform LDU decomposition, it's just related to the concept of solving linear equation through Gaussian elimination. So suppose you have a linear system. Okay. You want to solve, suppose the whole vector is X and Y. So the matrix B is given. Typically, like you have MZ equals B. Okay. But of course, hold on. This is the same as solve the whole matrix, at once. MZ equals B. Z is, the vector contains two partitions, X and Y. So if you write it down, and of course, A, B, C, D are, are blocks of matrices. So it means that you have like, let's say you have if X is 3, Y is 4, the whole variable number is 7. So now you can try to divide all those equations by 2 sets. Okay, I call it 1 and 2. Okay, the simplest concept in linear equation is that, how about, we get rid of one variable first. This is called, substitution. Remove one variable and make a substitution. Let's say if I want to get rid of if I want to get rid of Y in equation 2, somehow I need to normalize D so that, in equation 2, I get only only y, right? So I should multiply the inverse on both sides of equation 2. I get equation 3. But then somehow you want to subtract 3 from 1. So you should normalize 3, not normalize, you should multiply 3 by matrix B, okay? Okay? Then you get 4. From here, you see that you try to like make the two equations that have the same variable. So now you're gonna subtract 4 from 1. Then you get ax minus b d inverse cx equals b1 minus b d inverse b2. And now it reveals that this is how you will see a term that is very related to the Schur complement of D in the matrix ABCD. So this is basically the Schur complement. How it is useful, because if you have the Schur complement of a matrix, now you get equation 5. The equation 5 would be a linear equation that has smaller size than the whole equation. Now let me make a more explicit. So if x is 10,000, if y is just maybe 10,000, this is 10,000, z is actually 20,000. So equation 5 is an equation that the size of this is 10,000. Suppose I give you b, you can solve 5 because you can form a matrix S, cache it in the memory, and solve equation 5. Once you get x, from equation 5. How do you get y? You can get y from equation 3. Okay, y equals d inverse b2 minus d inverse cx. Okay, so you retrieve it from here. So the what? You see that the exploit of the Schur complement here would make sense, would save you some cost if the matrix C for example, if D is diagonal. If D is diagonal, it means that the operation here is very cheap. The inverse is very can be computed very fast, and the inverse can be cached in the memory. Okay, which also mean that you can form the matrix S cheaply as well. Okay, so the process here is actually a very common method in solving linear equation. This is Gaussian elimination, like we get rid of one variable to solve another variable first, and then once you get x, you can solve the other variable at the end. So this is one occasion that you might see the application of Schur complement. The second one is that if x is positive definite, okay, actually let me call it x sigma 1 1 sigma 1 2 sigma 1 2 transpose sigma 2 2. If x is actually represent covariance matrix, okay, so the Schur complement is given by sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 1 2 transpose. This has some meaning in statistics. This is called a conditional. Like let me give the problem setting like again here. Suppose x is given by this form in the yellow box. Suppose this is the covariance matrix of a random vector. Okay, suppose let's call it z. Z has two not two components, like two partition of the components Z1 and Z2. Okay. So the Schur complement of 2 block in X is given by the Schur the Schur complement of 2 of sigma 2 in X has a meaning that it is called the conditional covariance of Z1 given Z2. So typically, if the two variables, if the two sets of variable has these covariance, and if sigma 1, 2 is non-zero, it means that Z1 and Z2 are correlated, right? Are correlated. So you can explain part of Z1 by the fact that you know something about Z2. Okay, so conditional covariance matrix of Z1 is actually the covariance of Z1, but given the fact that the value of Z2 is fixed to a certain value. So how the variance, how the uncertainty in Z1 has changed once you know the information about Z2. Okay, this is a known analysis in Gaussian vector case. Okay, sorry, yes, Gaussian vector. That conditional covariance of Gaussian vector, you know, of one variable given another variable is actually in a form of Schur complement. Schur complement of two blocks in one block. Okay. So the results of Schur complement has many more applications. The context. So the contents can be found in any matrix analysis textbook. I'm going to explain more about the application when we in random process class, in system identification class and all. Okay.